But today we are here to attend the talk by Georgios, so talking about quantum computing memristors, how to advance their symbiosis. So George C.H. Sirakoulis serves as a full professor with tenure and head of the electrical and computer engineering at Democritus University of Thrace in Greece, and he's also now serving as visiting research professor in the University of West England and member of the Institute Laboratory of Unconventional Computing. His research emphasis on the future and emergent electronic device circuits models, architectures and systems, memristors, quantum, cellular automata, and so on. Unconventional nanoelectronics and computing, novel and emergent micro-nano systems and circuits beyond CMOS, computing devices and circuits, quantum computing, and quantum technologies, as well as bioengineering and biocomputing. His ongoing and recent projects on synthesis and performance optimization of a switching nano crossbar computer memory store, nanomaterials and electronic devices for quantum and neuromorph computing, wave-based memristive devices and circuits for classical and non-von Neumann information processing, holistic, fully automated nanoelectronic systems for health, monitoring of elderly people, paved the way towards the advancement of promising and emergent nanoelectronic systems that could alternate in an emphatic way the future of our society. So thank you very much again, Professor Georgios, for accepting our invitation. And the floor is with you to start your presentation.
Thank you very much, Ricardo. Thank you very much, Professor Reyes, for this invitation. Indeed, today's talk will be about quantum computing and memristors and how we foresee their symbiosis in a much advantageous way for both of them. So let me show to you how I foresee the future, taking into account the present. Here it is a simple metaphor of how cars, bicycles, motorcycles are moving in a fast but appropriate way, having almost a parallel manner in order for everyone to move in highways, in roads. And this is a metaphor of the data that are transmitted in our computers, and the same applies for the CPUs. And what we expect, the level of accuracy that we are having here should be as high as possible. And at the same time, we should be in order to have high volumes of data to be transferred across these buses, which in our case look like the highways and the roads that we're taking into account. So, in a sense, we are familiar with the fact that the swift pace of growth in traditional computer performance has hindered the development of novel computing techniques, as it has dominated both industrial and academic research. However, in tandem with the advancement of conventional computers, there has been an increase in the past 2 decades in the research community dedicated to exploring alternative or conventional computing systems that have the potential to suppress the capability of the von Neumann architecture. So this growth in conventional computing research has occurred as the growth rate of conventional computers has slowed. And in order to identify successor technologies to existing computers, researchers are exploring, first of all, beyond CMOS technologies from the circuit design perspective and beyond von Neumann architectures from the computer architecture perspective. How the things are going with the conventional CMOS and the limitation that we are experiencing nowadays, it is shown here. And this is exactly what fuels the model computing task of AI and especially quantum computing, And researchers are trying to explore several alternative technologies such as spintronics, photonics, and memristive devices, among others, so as to reduce the power consumption, to increase the processing power, and as well to enable a new computing paradigms. So, in addition to what I have already stated, we can also mention here the memory wall problem, which refers to the bottleneck that arises between the CPU and the memory, as the speed of memory access has not kept pace with the increase of the CPU. And all that brings to us to a new, let me say, era where we are looking for the beyond CMOS technologies, something that will be able to advance the memory and computing capabilities of today's computer. This exact what we are having in mind is what we call Memristor devices. Of course, Memristor devices have emerged as a great candidate for the acceleration of traditional CMOS system as standalone computing system for various applications. And if you ask me what are these Memristor and nanoelectronic devices originally postulated by this Professor Leon Chua, can be described as two terminal passive circuit components that are able of adapting their electrical conductance in response to voltage, while also retaining their conductance value as long as a voltage is not applied, constituted what we call a non-volatile memory element. As you can see here in the table, there is an ever-growing attempt to fabricate memristor devices, and we're taking into consideration, we are utilize different physical mechanisms, such as you can see here, the ferroelectric RAM, the spin transfer, torque magno-resistive RAM, phase change, and many more, included what are the most interesting here, the conductive bridge RAM. This demonstrate, and they are all described under this guide, different advantages. And among them, the ones that shows case the most emphasizing characteristics, I consider the CBRAMs that has emerged as a great candidate for a resistive non-volatile memory, but also for in-memory computing element. So in order to design them, we need models. But before going to the fabrication and the modeling aspects, let me also introduce you some ReRAM market perspective as introduced by Qubit, an Israeli company which is specialized in the fabrication of the ReRAMs. And as you can see here, they are foresee a very interesting, almost exponential growth of the ReRAM devices to be supplied in the market in the very next years. And what makes this perspective as truly interesting is like the work that is shown here by Xanfei Xia, recently elected by the IEEE and the NTC Council Fellow, who has demonstrated that a Memristor crossbar with a single layer density up to 4.5 terabytes per inch square, they are an order of magnitude denser than the state of the art, which is the 64 triple level cell NAND flash technology. And the memristors that are shown here in the crossbar, which are 2 times 2 nanometers square, nanometers in size, they are capable of switching with just tens of nanoampere electric current. So what they have managed here is to introduce really tiny nanostructures based on what they call nanofins, which are fabricated with special deposition techniques, and they manage this to have very low resistances below 100 ohms per millimeter and 10 times less resistant than a 10 nanometer. Here are the exact white CU wires that I'm looking for, and I'm now making the comparison. And this can definitely um, pave a new way of how we should have new technologies of memories in our PCs. So, due to the fact that although there are, as mentioned before, industries that like Qubit or GNOME, which is also a very well existing memory, we need most of us models that are much appropriate to describe the functionality, the operation of these devices. So the behavior, we have now two categories basically for the Memristor models. And the first one is the behavioral model, which describes the device expected action, responses, and outputs based on specific inputs or stimuli. And it focuses, as it is saying here in slide, on capturing the high level functionality and behavior of the device, rather its internal workings or implementation details. And we have the physical one, the physical models, which can be divided to microscopic models, and these represent devices at a rather small scale, focuses on the fine details of their components interaction. And you can see also here the macroscopic, which on the other hand represent devices at a larger scale, considering their overall structure, geometry, and behavior. We have worked as a group many years on these exact models, implementing and bringing to the researcher attendance several different models, either coming from mathematical, behavior, or even physical point of view. Here in this work, we are going to show to you how we can model CBRAM, the one devices that I prefer to use as mesonym to their pronounced advantages, and we are going to do that with the help of quantum mechanical processes. The switching in CBRAM devices to the on state and reset of states are believed to be resulting from what we are seeing here as metallic filament formation and disruption, respectively. Here you can see, according to the IV characteristic, the steps that were following in order to start initializing the device with an array of state by applying some positive voltage where in position the metallic atom to start to infuse into the dielectric, so they are forming a conductive filament. And after some time, when the top and the bottom contacts are short circuit through the filament formation, the device will finally switch out to what we are called as iron, and this is the final state as shown here. By applying now a negative voltage, the metallic atoms are pushed back, and you can see that the filament ruptures, leading to the device to what we are calling here the arrow state. Here you can see what is the process that we are following, and we have started with a very capable computation tool provided and inspired by the same man who we are talking about, von Neumann, about the computation architecture. This is the cellular automata computation tool. So we have introduced a filamentary-based nanoscale Memristor model for the ASIM devices that has been developed following the exact ideas introduced by Valoff and his team in Wasser group. And the model assumes a standard metal insulator RS device in two-dimensional, and the ion kinetics in this the electric that results in the filament formation and deformation are modeled using quantum walks, which incorporate the applied potential distribution in the filament. We didn't make only the model, but as you can see, as I should say, with the help of our colleagues in Democritus, we were able to fabricate and measure these isolated metal insulator devices. Here, as you can see in the slide, for a cell to become copper, as it is shown here, there are three things that have to be fulfilled, and these are shown here. You see that there should be a positive applied voltage, there should be a Cu atom next to the atom that we are taking into consideration, and most important, the threshold value should be less than the probability so as for the state of the atom to change in the Cu condition. Here you can see how this effect of the voltage applies to the Cu atoms and the formation of the filament. And as it is shown here in these exact diagrams, the relation between the voltage and the probability for the copper atom to jump into or leave the dielectric material is not linear at all. And a suitable approach for that is to use an exponential equation, and this is related to two quantities. The value of C is the one which determines how abrupt the equation will be, and for the case of the study, we have chosen to go with value of 2. Having all that said, the applied voltage is also distributed across the device in a linear manner. This means that the cells that are closer to the upper contact have a higher chance for a copper atom to jump into or leave the dielectric material. In combination with the previous equation that was described, the final probability arrays have been created. Then, and on to the fact that we are talking about quantum phenomena that we are taking into consideration, a very useful and accurate way in order to measure the conductance in a nanoscale device is this NEGF, the non-equilibrium green function. Probably I should have put some reference here, but I believe you are all familiar with that. In order to calculate the conductance of the device through the NEGF model, there are three parameters that need to be known. The first one has been already expressed. This is the atomic structure of the device, which is calculated from the CA-based algorithm. And then we have to take into account the hopping energy and the retention energy of each atom. Using this parameter, one can derive the Hamiltonian array of the device. And as said before, we are able, with the help of this equation and the resulting energies, to solve the NEGF into our device, the fabricated one, and to produce the model as it is shown here with the exact IV characteristic. But there is a tiny problem on that. The problem is that one of the major issues that are resulting from the utilization of the NEGF method is that when we are doing these memristive calculations, there is a request for high performance computing resources. In order to tackle this problem, because NEGF is usually, as you are aware, a real computation-intensive method, and then acceleration is necessary. So the model has been ported in a GPU, and compared to the CPU, the performance as shown here is the high speed is enormous. We have just, for different grid sizes, just a linear increment, and this is very, very useful compared to what we experienced with the CPU. And not only this, but you can see here how our model is developed, and you can see the time evolution of the filament exactly at the same time with the time evolution of the applied voltage. And most important, you can see how the IV characteristic in logarithmic scale is progressing, and you can see that it is very, very, let me say, close to a realistic behavior of a device compared to other models that exist in the literature. And this is a pure advantage that is coming with the adoption of this quantum characteristic that I mentioned before. But not only this, as you can see in this slide, we have moved towards and we have enriched our model. And namely, for this fully quantum model, the CA filament evolution has been replaced by the quantum walk filament evolution. The quantum walks are, I can say, quantum analogs of the classic random walks. These are mathematical objects which are frequently used in simulating phenomena. In our case, because we are in the nanoscale territory and many quantum phenomena arise, the quantum walks were adopted and the probability is distributed through the appliance of the shifting operator and the Hadamard gate, as is shown in this equation, to the coin. And because with the random walker we are flipping a coin, and this is what we're doing here with the help of the Hadamard gate and its application to the coin. And in this model, a position with probability higher than a threshold is occupied by a CU atom. And here you can see the filament evolution due to the quantum Walker probability distribution and the initial, let me have the pointer, the initial filament growth with positive applied voltage give its turn to the degradation of the filament due to the applied negative voltage and the termination of the filament. Furthermore, you can see here which are the key, let me say, parameters, and we are proposing them through these IV, logarithmic IV curves. Firstly, for different the electric retention energy, the ones that we are called EDO, logarithmic IVs for a range of the electric retention energy between 10 electrovolts and 11.6. And you can see that we are also experiencing the same for the metal retention energy here between 7.1 and 8.7. But why we are talking about this parameter? The fact is that the higher that the electric retention energy is, the better is the insulator. And what does that mean to us? It is less conductive. And similarly, for the other diagram, the higher the metal retention energy it is, the higher is the resistance of the metal. So these two variables can manipulate the electron transport and therefore are acting as the fitting parameters for our model in order to regulate the R-off and the R-on states of the fabricated devices. Talking about fabricated devices, let us show to you how these correspond. We're having here the simulation, but also the real results. And you can see for different cases, we have been able to manage to reproduce in a very fine agreement with our simulation tool the exact experimental results of the fabricated devices, the one that were fabricated in our national research center of Democritus, located in Athens, with the help of our colleagues, Dr. Panagiotis Dimitrakis and his team. So we were talking about the memristors and how these devices can be really helped by the computational power of and the quantum characteristics that are found intrinsically into the memristor devices, and how we can combine the quantum techniques, computational techniques, in order to advance the level of modeling. But our most interest is how about if we can go the other way, if we can use the memristor in order to model the and accelerate the quantum computing systems. Talking about quantum computers, let me give you a short introduction. Probably the origin of the term belongs to Deutsch, who said that a quantum computer is a type that use the principle of quantum mechanics in order to perform computation. The most famous computing systems are nowadays the classical ones and the quantum computers. So in the classical computers, we have the smallest unit, which is the bit, and the processing of the data usually happens till so far in a sequential or semi-sequential, let me say, manner. But in quantum computer, we have the smallest unit of information to be called qubit, which in contrast to the classical bit can be any intermediate state between 1 and 0. And the processing of data is in the quantum computer is happening in a parallel manner. Application, too many, but instead of saying the application, let me give you an idea of this very recent review. And you can see that in the last decade, the number of the companies which actively develop quantum computer hardware has quadrupled. In 2022, multiply funding rounds surpassing 100 millions of dollars have been closed, and the transition from the lab-based toys that we had in the past, now we are going towards commercial products, and this has just begun. The competition is building not only between different companies, but also between different computing technologies. There are many researchers who are really experts in the field, and now they are working on building such quantum technological miracles, if I can say, for these new quantum computers. But the idea is that we have to cover still a long way. Here you can see the IBM quantum computing roadmap, but also which is the forecast and what they expect to experience, to build, to fabricate in the next years. And you can see that we are really close to have a new evolution, a new era in the computing history, and that's all thanks to the quantum computer. But are things so, let let me say, optimistic. The fact is that, yes, there are limitations of physical computer, quantum computer, in order to be able to solve these complex problems. Quantum algorithms have to be developed. The testing and the development of these algorithms are not trivial in fabricated quantum computer, and I can name a number of that. I started with IBM that I mentioned before, so we have the Q system. One, we have the Google quantum computer. If I remember right, called Sycamore. We have IonQ, D-Wave, Xanadu, Alibaba, too many quantum computers. But why I mention this is not so trivial for these algorithms to be developed in quantum computers. First of all, due to this, the coherence of the quantum systems, as they even slightly interact with the environment through the effect of temperature or other electromagnetic signal. Also, the scientific community in general does not have, let me say, an unlimited access to this fabricated quantum system that I referred before. And for this reason, the development of quantum computer, not to say that it comes with a high fabrication and maintenance cost. The development of such quantum computers contradicts to what we are preferring nowadays to do, mainly to develop quantum computer simulation, which is easier, less expensive, and probably it is also the floor for new scientific revolution. Here we are coming with our proposition, and this is a Memristor-based quantum simulator. For doing so, we need to represent the qubit, and the qubit is, as I said before, the fundamental unit in quantum computers corresponding to what we had as bit in classic computer. Let me give you just a small, very fast overview. So we start with the representation of the qubit, and according to this expression, the state of the qubit is a vector in the block sphere, and which the radius of which equals to unity. We start the qubit vector initial point in the center of the sphere, and the terminal point lies on its surface, and we have two angles, theta and phi, which determine the direction of the state vector, while the two base states are the pole of the sphere. We have in here the 0 ket and the 1z and the 1 ket as named. So the qubit can be in every superposition of its two base states, so it has an infinite number of superposition states consisting of the combination of these two base states. In order now to perform calculation using real circuits, the problem is that we have to separate the imaginary value as shown here. To do so, we're using the Euler's equation. We separate the imaginary and the real part of the base state 1, and we finally have three different, as shown here, real factors, which fully represent in total the qubit state. The first two ones, the A and the B, describe the real part of the base states 1 and 0 accordingly, or 0 in 1 to be more precise. And the third M, C, describe the imaginary part of the base states 1. So during quantum computation, the qubit state evolves with time. The state-time evolution is represented by the time evolution of which? Of the two angles, theta and phi, and the idea is to represent the state of the qubit, as it is shown here, and its time variation with the input voltage of three memristors, namely in our case V1, V2, and V2 and 3, all dependent of the time. By storing the qubit in a medium, for our case, the Memristor devices, we will be able to explore real circuit quantum computation, at least as it is shown here in simulation level. Ideally, for the mapping of these three voltages, we would need a Memristor device which is performing in an analog manner. For terms of simplicity, having in mind the some difficulties that are arising with the fabrication issues of the Memristor, we will start trying to use the binary switching Memristor in order to tackle this problem in circuit level. But we are not done yet. We have two more problems to solve. The first one is the fact that the Memristor needs to be proportional to the voltage, but this means that we should have a rise in voltage and they should correspond to increase in memristor, while a decrease in voltage should correspond to decrease in memristor. And by applying directly the voltage to the corresponding memristor, apparently the change of memristor values do not imitate necessarily the waveform of the voltage. In order to achieve this analogy, we have what we call here a circuit implementation that correspond to this theoretical description to an active differentiator, as it is illustrated here, and the voltages are applied here, and at the output we are taking its output and we apply it to the memristor. The second, we have here some factors that are used in order to manipulate the changing rate of the devices, just in a circuit level. The second problem is that we have to address that the two-state memristor does not provide enough resolution. Here, taking into inspiration from another work that we had some time ago, we have designed a multi-state configuration memristor. We managed, as shown here, to have 8 different states implemented in memory with just 3-bit resolution, and here we have 9 branches. The first one, it is only resistive, while the other have an uneven increasing number of memristors, enable us to have a bigger resolution as the one requested by the representation of the qubit. By applying now every voltage to the differentiation, we have an 8-state switch, and we achieve a mapping between the input voltages that they describe the qubit and the memristance. This is the most important of these multi-state switching, multi-state switch, and here are the exact simulation results for every gate. We have also shown here that this is possible for the other voltages, the other 2 voltages as well, as shown here, and you can see that in every case we have the memristors to follow the voltage, and this is what we aimed for. And since we were able to reproduce the qubit in a memristor with the memristor devices, let us check which will be the next steps. We are now in position to let me say replace the quantum computer simulators, like for example the one that we are using, the Microsoft Liquid or the famous IBM Qubit. With let me present now the memristive quantum simulator. For doing so, we need quantum gates. We will take into account for this memristor-based hardware memristor crossbar in order to perform this vector to matrix multiplication, which is needed in order to execute the quantum gate. And this will be depicted in the memristive crossbar, and voila, we are having our quantum memristive-based simulator. Starting before that, I mentioned how we depict the qubit, and in order to change the state of the qubit, we apply a quantum gate. By consequently applying this for a greater number of quantum gates, we can implement what we are calling and are found in literature as quantum algorithms. Here you can see, in terms of mathematical representation of the qubit and quantum gates, that in linear algebra, the qubit is represented by a column vector, and the coefficients of the basis states are the elements of this column vector. These are the most well-known gates. We are talking about the Hadamard and the CCNOT, and the quantum gates are represented by unitary matrices, which size is determined exactly by the number of the qubits. What we are looking for is to have more qubits, because these are not usually available in the commercial, or let me say in the general quantum computers that we are having in our hands, and this has been also shown in the forecast of the IBM and what they are looking for to increase the number of the available qubits. The action of quantum gates on qubit is performed through this, what I'm showing here, matrix vector multiplication. And this is a very useful, let me say, idea, because based on the multi-level resistance characteristic of the devices that I proposed before, we have now the opportunity to save this matrix data into the memristor cells, which in other way we can say that realize the matrix vector multiplication with 0-1 time complexity, merging all cell currents in each row through the Ohm's law. And the next step is to evaluate if a universal set of quantum gates can be implemented by this, let me say, Memristor binary Memristor crossbar, taking into account the reprogrammability of the Memristor and the Memristor crossbars. As before, we have the binary Memristor and the universal set, which is comprised from Hadamard and CCNOT gates, is rather promising in order to implement quantum computations in this Memristor crossbar. Please take into account that, as has been shown before, it will be shown in the next slide as well. In the Hadamard gate, we have a negative value of -1, and so the crossbar should be able to represent also negative values. This comes with an overhead in the number of columns that we are going to use and the number of the memristor. But seeing that, I will progress to the next slide. And here you can see which is the Hadamard gate crossbar, and the crossbar equivalent of the 1 qubit Hadamard gate consists of a 2.4 memristor configuration. And I forgot to mention that we are also going to use these differential amplifiers because they are used for the -1 that we are going to somehow depict in our matrix representation in the memristive crossbar. The simulation results of the programming processes are presented here. You can see that during this process, all the memristors are initialized in out of state. We applied a negative Verised voltage to every row. And finally, for the selector transistors, we are coming up to these are switched by with the V selector equal to a certain voltage pulse that we have programmed, and then the crossbar is programmed column by column. And during the matrix vector multiplication, all memristor contribute to the calculations, such as every column of the crossbar is selected by applying the vessel to each one of the transistors that I mentioned before. This simulation of the computational process is highlighted here with the red square, and is labeled red. And 4 different input combinations are taken into account for the inputs and the outputs in order to prove that we are able to implement the Hadamard in the crossbar. And we are following the same technique as before for the CCNOT. Here the main difference is that we don't have any negative values, and this makes things even more easy for us, but the whole operation, it is almost the same. So we are in position to reprogram the crossbar to depict either the Hadamard or the CCNOT gate quantum gate implementation. And here you can see, with the help of sub crossbar, if I can use this term, we are in position to implement a generic quantum circuit. And you can see the generic representation of the differential crossbar, which is capable of implementing an n qubit gate. And the crossbar dimension will finally be in accordance to the different basic states of the used qubits, and it will be equal at the 2 in the power of n, which is the number of the qubit. The general configuration is here. It is the multiply memristor sub crossbar what we are using, and it is capable of simulating various quantum circuits. But not only that, and this is a spoiler alert, but also to implement different quantum algorithms, such the very well-known algorithms of Deutsch and more. Here you can see that we have developed also a Memristor framework, and utilizing this crossbar configuration, this GUI helps the user in order to choose one after the other the first of all, the number of the qubits, and secondly, you can also declare the number of the computing steps. Every step consists of a combination of quantum gates and the Kroninger product of the computer gates of a specific steps calculate the total quantum gate result. And this is an example of the quantum circuit, which is demonstrated to describe the functionality of the framework. It is a qubit, as it is shown here, computation starting with a Hadamard and a Pauli gate for the first step, two Hadamard for the second, and CCNOT gate for the third. And with different colors, in blue color you have the Aaron Memristors as shown here, while with the yellow color indicates the R of Memristor, and the number of the crossbar, I forgotten to say, it is equal to the number of steps each one represented to what we had in mind in order to make this calculation. And here you can see that we have the right voltage figure tab and the programming signals that we are applied to each of these sub crossbar in order to program them. And as said before, the crossbar dimension equals to the number of qubits. In our case, we have 2 qubits, so we have 4 times 8. These are the final crossbar that we are going to utilize in order to succeed our calculations. The final, the penultimate tab named quantum computation, it is the one which shows the quantum calculation, and the crossbar have been programmed in order to represent our quantum circuit in the previous steps, but also in order to perform quantum computation by choosing various input qubit states that will be inputted to as a voltage vector to our crossbar circuit. Remember that our example is a 2 qubit circuit, so we have 4 different input combinations for the basis state that we can examine. In this slide, what I'm showing here, the input combination is 0, 1, and it is demonstrated with this output result, and we can confirm the exact right simulation result. Here you can see, last but not least, how you can modify the parameters of the model. We have used different models, the standard rating, which is a mathematical oriented one, very well known to the memristive researchers. Then the very famous Stanford model, as it is shown here. You can change through the GUI the parameters, and you can study the functionality towards this parameter of the Memristor crossbar circuit with the appropriate Memristor model that you can easily implement through this, let me say, framework. Now, which is the takeaway message? So you can see, you have seen here that the quantum modeling of Memristor devices, and especially we focus on CBRAM devices, has been made possible through the quantum computational techniques. And moreover, we have gone all the other around, all the way all around back, and the CBRAM devices have been also exploited in order to represent the qubit state. Having this in hand, we were able to, with the help of memristive crossbar grids, to implement circuit-based quantum computation. We have implemented different gates. We were in position to reprogram our crossbar and to represent different gates. And most important, beyond going to the framework, something that has just arrived, it is under now final review, you will find out that we are in position now to implement every quantum algorithm, and the most well-known are already in this paper, which will be published really soon. There you will see that our simulator has been enormously accelerated compared to the other hardware implemented quantum simulators, either on FPGA or CMOS technologies, not to mention that we are much faster compared to other CPU-based or GPU-based quantum simulators. And we have provided a framework which is free for the audience to take it into heart and to experience how this quantum-based Memristor simulator works. All this thanks to my team, especially Agelos Firigos is the one who was in lead of this research for the last year, but also all the other guys here played and girls played a very serious role. And many thanks to our partners and funding. And that's all for me. Thank you very much for your attentions. I will be glad to answer any questions. Thank you very much.
So thank you.
I tried to be on time. Hopefully, I wasn't so
Yes,
late.
great. So if anyone has any question, please do your question using the chat channel as soon as possible. I'm seeing no questions for the moment. But so I have one. What about the scaling of this, the use of?
The fact is that we are now in process to reprogram in a semi-parallel way this crossbar, so as to have a linear than exponential in correspondence to the number of the qubits that we are looking for. We are very close in order to have it coming in our memristive crossbar, and we believe that this reprogrammable pulsing protocol that we are using will be efficient to lower the exponential increase of the usage of Memristor crossbars to almost linear, so as to be able to take full advantage of the technology. That's very good question, and it is exactly what we are working nowadays. It is also beyond what we are going to have published in the next months.
Okay, any comments, additional comments about power consumption?
Yes, the power consumption is not our best, let me say, card in the table. We are almost competitive to what the other hardware simulators propose. We are very close. We are talking about, we have examined also the energy, but also the power consumption in matters of baht. But we are still talking about this very well known, like the Grove and Deutsch algorithms about nanowatt. So I believe we are in a good starting position, but also we are much better. We are doing much better in execution time.
Okay, thank you. I'm seeing no questions in the chat. Just some comments that your talk was a very interesting one, and so if someone has still a question, you must do it now.
Or you can send me an email. I have also provided my mail. It is exactly the same, but just replace the first dot that you are seeing, gsirac at ee.duth.gr. So it is rather easy. If you have any interest on that, I would be rather happy to answer.
Okay. Well, so thank you very much.
Thank you very much for giving me the opportunity just to show you our upcoming research. It was a very nice opportunity, and I do appreciate your kindness for providing us this floor with this excellent series of seminars. Thank you very much, Professor.